approach. I will cover the first two sections, and Bertrand Guenet will cover the modeling approach. This project started in June 2022.
Marta, I think you're not sharing your screen.
I will try again.
Now it's loading.
Okay, let me know when it's ready, please.
Yeah, perfect, Marta. We can watch it now.
Okay, perfect. So as I was saying, this is a collaborative effort of 21 institutions located in 8 European countries and 2 associated countries. As I was commenting, the presentation will give you details, or we will give you details through the presentation regarding the concept of the project, the model inputs, and the modeling approach. I will cover the 2 first sections, and Bertrand and Guenet will cover the last one. So the project started in June 2023. We are focused on developing a tier 3 MFV system. And we have highlighted here 3 main research questions, but obviously we could highlight many others, and probably during the presentation you will hear some more apart from these, which are derived from these main 3. And the focus of the project is on quantifying and analyzing the impact of carbon farming practices within different circumstances in terms of climate and management practices, and see how those carbon farming practices impact soil organic carbon accumulation. Then we would like to know how to measure this accumulation in a robust, scalable, and cost-effective manner, and how this accumulation changes within different climate change scenarios and socioeconomic conditions. The project is implemented and based on 3 main pillars, which are related to the MFV system, and identify key available in situ data and develop remote sensing indicators, which will be further assimilated into process-based models. We are also considering the socioeconomic part, which is the 3rd pillar. So the first one would be data harmonization, the second one, the modeling approach, and the third one, the analysis of those socioeconomic impacts and the cost effectiveness of those tools. All those conclusions and results will be highlighted in recommendations and guidelines and further disseminated. So the general objective of the project is focused on developing a comprehensive and robust tier 3 methodology that would be scalable, accurate, transparent, cost-effective, and reliable. To do so, we have nailed down this general objective into 6 specific objectives, which are related to estimate the accumulation of soil organic carbon in 9 European representative land use land cover classes, to assess the effect of those carbon farming practices, to analyze the accumulation, as I was mentioning before, considering different climate change scenarios and socioeconomic conditions, so that we can highlight specific variables and key methods to develop this robust, transparent, and cost-effective methodology at different scales, so that we can unlock results-based payments, and all the process is focused on stakeholder engagement, so that we help farmers increase their faith in voluntary carbon markets. To achieve all these objectives, we have selected 15 demonstration sites, which are located in 5 European countries and 1 associated country, and we are covering 5 biogeographic regions. Within those land use land cover classes, we highlight croplands, grassland, agroforestry, forest, peatlands, and peri-urban areas. Our methodology is a bottom-up approach. Those components were also highlighted in well-known scientific papers, such as the one from Peter Smith, where they were highlighting these in situ data, remote sensing, and modeling approaches. The main focus of this project would be to identify key ways, key methodologies to upscale this methodology in a, as I was saying, robust, transparent, and cost-effective manner. So to do so, we have identified long-term experiments where we have in situ data, and we are developing those remote sensing indicators that will be further assimilated into widely used process-based models at sub-landscape scales, which means that we will need to identify key lessons to improve process-based models that can be applied at large scales, and also considering different climate change scenarios, different management scenarios, and also take into account this cost-effective approach. Not all the process-based models are in the same situation and are not developed to cover and achieve that objective. That's why we are just considering widely used models at sub-landscape scale, and afterwards we will carry out some of those analyses at landscape scale with one model, which is Guenet. Then we will provide specific recommendations to scale up this methodology at national and European level. So this hybrid MFV system, including in situ data, remote sensing, and process-based models, would follow the following workflow, which would be, as I was saying, the identification of in situ data, the development of key remote sensing indicators, but then we need to understand how many of those indicators are playing a key role in the model performance, and therefore we have carried out already a sensitivity analysis to understand the uncertainty propagation. As part of those model inputs, we have different conditions, and in the reality, when those MFV systems will be implemented in an operational manner, there would be different management, land use histories, different initial conditions that we would like to account in this research and innovation project. That's why we have considered all those demo sites, 15. We have carried out different indicators, although you will see at the end, not all of them will be the key ones, let's say, because obviously not all the models are accounting for all the different parameters in the same manner. And then we have carried out a field campaign in 2024 and also in 2025. As part of this selection of indicators, we have considered a stratification according to soil associations and pedoclimatic conditions to understand how those in situ boundary conditions can be compared within different management scenarios, business as usual, and different carbon farming practices. And from those, we have selected, as I was saying, specific remote sensing indicators to substitute those in situ boundary conditions into the process-based models, and carried out the model parameterization, the sensitivity analysis, and the further uncertainty propagation. Also considering the impact of socioeconomic assessment and the cost effectiveness of those tools. As part of the indicators that could substitute in situ data, obviously remote sensing needs in situ data for calibration and validation purposes. There are climate management, soil, and vegetation parameters. Within the we couldn't show all of them today, but we have highlighted the background biomass and dry matter biomass because it's integrating all these different components. And as part of this, we have developed a GMV, NASA CASA model, which is a light use efficiency model that is providing an estimate of NPP, of net primary productivity, which accounts for the amount of photosynthetically fixed carbon that can potentially be accumulated, sequestered into the soil. And for that, we are using factors that are coming from from widely used and implemented equations, such as the ones highlighted by Bollinger. And here with those factors, we are also accounting for the background and below ground biomass. Here, what we have done is that at sub-landscape scale, we have identified the accumulation of dry matter biomass. Here you have one example for winter wheat, and we have established the relationship of the analysis at sub-landscape and landscape scale to extrapolate this methodology to larger areas. And obviously, this is only one crop. We have many others, but what we are trying to identify is that how many of those crops would be declared within the Common Agricultural Policy. Farmers are declaring the main crops. So basically, what we would like to understand is that these kind of approaches could be applied later on in an operational manner, as we were saying, in a robust, transparent, and cost-effective approach. So the main conclusions and the main take-home messages of this part would be that process-based models must be calibrated, parameterized with in situ and remote sensing data. Remote sensing data and tools as well are very useful for the scale-up analysis and to reduce the cost of this implementation. And to do so in a robust manner, we really need to understand the errors included in that in situ data and how these uncertainties propagate into a process-based models. You have seen that we have provided some error metrics, but Bertrand and Guenet will follow up this information through the model approach, giving you more details on that. So please, Bertrand, the floor is yours, and let me know whenever you want me to change your slides.
Okay, thanks, Marta. So yeah, we can go for the next slide. So basically, I will try to explain you the modeling approach we propose for the moment at the sub-landscape level and how we can propagate uncertainties in those models. So here in the example I will show you, I will use the ROTC model. So the ROTC model is a model that was developed by the Rothamsted Research Center in the UK. It's a very, very famous model, quite used in the soil science community. The idea is that it's based on the schematic that you can see on the left side, where basically you divide the soil organic carbon into different pools. You have inputs from the plants or from organic fertilizers that you then divide into different pools, like decomposable plant material versus resistant plant material, and then this is decomposed and recycled into the different pools. The mathematical behind, I will only have one equation in the model, but I think this one is really key. It's based on first order kinetics approach. So basically the decomposition of a pool depend on how much carbon you have in this pool and depend on key decomposition parameters, which is called K, which is the decomposition rate for that given pool. And then you have some rate modifier that depends on the temperature, on the moisture, and on the soil cover. Next slide, please. Can you go to next slide, please? Thank you. So basically what we first did is that, okay, we wanted to know how the model projections are degraded when we use boundary condition of the model which are not directly coming from ground truth data, because all the models you can use have their boundary condition, and you have to provide them with this information if you want them to run. So in the case of ROTC, for instance, we need some information on the climate, we need information on the soil cover, we need the information on the carbon inputs, on the clay content, and also on the baseline carbon. So basically we designed these simulation protocols that we call simulation 0. It's the first line. You have all the boundary conditions that are really directly coming from the site data, so it's measured on the site, and then you change one by one each of the boundary condition by a remote sensing product. So for instance, in simulation 1, you take climate from a reanalysis. So in our case, we choose to use the ERA5 length reanalysis. So it's not directly measured on the site, but all the others, they are directly coming from the site. And then the same for carbon inputs and so on and so on. And at the end, you do a simulation with everything coming from remote sensing product. So the idea behind is to try to understand, okay, if you want to upscale your modeling approach at the landscape level, you won't have all the needed information to run the models for all the given grid cells of the region of interest. So you would need to use remote sensing product and how the model projections are degraded in that case. So we can go to next slide then, please. And so that's basically what we have here. So this is the difference between the different simulations. So model 0 is always our control. So with everything coming from the ground truth, and then it's you have the effects on the y-axis, on the x-axis. Sorry, you have the effects of replacing a measured boundary condition with remote sensing data after 10 years of simulations. You can see, for instance, that when you replace climate, so model 1 minus model 0, you reduce a bit you have a bit less carbon projected by the model than when you use direct climate. Also something that I forget to say, sorry. Here I'm showing you the example of one demo site in Belgium. It's the Lonze site. It's in Wallonia. It's a cropland for a very, very long time. Very, very classical crop management over there. But this approach will be done in all the other demo sites of the project. But we just focus on this site for the presentation. Okay, so let's continue. No, sorry, can you go back to the slide before, please? Then something that we see here is that the biggest difference we will have are actually when you change the carbon inputs, whatever, if it's through the main crop or if it's the cover crop. So basically when you do model 4 minus model 0, model 5 minus model 0, and so on. So we had tried different things to replace it, but it's basically the message is the same. The model is quite sensitive to the carbon input. So thanks. You can go to the next slide, please. But the point is that, okay, you know that the model is sensitive to this, but all those remote sensing products, they are also coming with their own errors and uncertainties. So it's important to also try to propagate those uncertainties in the model prediction to be able, if we can detect any change in soil organic carbon stocks with different carbon farming practices that could be implemented by the farmer. So there is a lot of options that you can do for uncertainty propagations. We decide to use the Monte Carlo approach for a couple of reasons. First, because it's a very classical approach. So a lot of people in these fields, they know the methods. It's quite accepted by the community. So we don't need too much to justify why we use this one. It's a very classical approach. And also it's a very simple approach to implement, in a sense that it's basically you run your model again and again and again, and you just sampled randomly the value of your boundary condition in the joint distribution of its of this given boundary condition. So it's relatively easy to implement. I will explain more details later on, but this is basically the main idea. So you can go to next slide, please. So yeah, this is basically how it works. You have your remote sensing products. Here, the example of the carbon inputs, it will give you an average for a given grid cell, but also it comes with its own errors. So you have a probability distribution of the value of these carbon inputs. So can go to the next slide. Then the idea is that you randomly sample a value inside the probability distribution a quite high number of times. So it can be 1,000, 10,000 times. It depends on the model needs. You can go to next slide then. And then you run the model n times with each time a different value for carbon inputs that was sampled inside the probability distribution. Okay, go to next slide. And at the end, what you have is that you have how the uncertainty related to your carbon input prediction from remote sensing will impact the soil organic carbon prediction you have. And so you can predict the mean of the soil organic carbon prediction from the model, but also the confidence interval, which is here represented by the error bars. So you can go to next slide. So as I was telling you, the models, they have several boundary conditions. So maybe you could be also be interested to what is the contribution of all of them. So what we did is that we did simulation where all the boundary conditions are run the way I just explained you, so with uncertainty propagation, and then we do the same, but we fixed the clay to the average, or we fixed the temperature to the average, or we fixed the carbon input to the average, and so on, which makes that at the end, we are able to estimate the single contribution of all the boundary conditions in their uncertainty propagation. So you can go to next slide, please. So what we did in this exercise for the moment is that we just consider carbon farming as an increase of carbon inputs. I think it's important to keep that in mind. It's a quite oversimplification of the reality, but for those simulation, carbon farming is only an increase of carbon input. So we do not change anything related to the hydrology of the system. We do not change anything related to carbon exchange, cation exchange capacities or whatever. It's really just an increase of input. We have 3 scenarios and a control. So basically you increase the input by 20%, 50%, 150%. And we did also the same, but we had something on top of it, is an increase of temperature. So it's an increase of 5-degree average. Also, it's a bit an oversimplification of the reality, because obviously climate change is not only an increase of temperature everywhere at the same level, but it's more some kind of an idea to understand how the model behave. And we again repeat all these carbon farming scenarios. And so we propagated the uncertainty for all the boundary condition I explained to you, and we also did it for each single boundary condition to estimate the contribution of each of them. We run the model over an 11 years period, and then we consider that we have differences between scenarios where there is no overlap between the 95% confidence interval that I will show you later. So you can go to next slide, please. So this is the first set of simulations. So climate is the climate observed for this period. We have in blue the control, so we just keep the value as it is from the remote sensing. We have then in red the scenario with a 20% increase, in green 50% increase, and in pink 150% increase. The brown point you see in the middle is a measurement that was done in that site at that moment. It's interesting because it's basically show us that the model is really giving you a good soil organic carbon stocks for this site and for this period. But you can see also that the confidence interval from the measurement is also relatively spread. But something that you can see here is that, okay, basically, as I was telling you, you start to say, okay, I see a significant differences between my scenario when my confidence interval do not overlap anymore. You can see that, for instance, for the scenario with a 20% increase, for the entire simulation periods, the confidence interval, they always overlap, which means that with such a tool, you're not able to distinguish a change in soil organic carbon stock, if you have a scenario when you only increase the input by 20%, and this is due to the uncertainty of the boundary condition you used. If you go to next slide, please. For the green scenario, so plus 50, you can see that you start to see something around the year 2019, 2020, 20 more or less. So the confidence interval, they start to don't overlap anymore. So it took you basically between the 5 and 6 years to see a difference. But obviously, when you increase by 150%, the increase is so high that you see a difference very, very quickly. So it basically tells you that you have this uncertainty that propagate in the model predictions, and that make that you have to take this into account if you really want to use process-based model for monitoring, reporting, verification. So when we look at the relative contribution of all the products, it's interesting to see that if you remember what I was saying before, for the sensitivity analysis, we said that the model is quite sensitive to the input. If you change the input, it reacts quite quickly. But since the errors we had on the input was not so big, the relative contribution to the uncertainty in the model prediction from the input is not so important. The main contributors of the uncertainty, they are the clay contents and the precipitation. So why the precipitation? Basically, I was telling you that we are using the ERA5 reanalysis product. How it is processed, it is basically some methodological models that are run and that are where there are a bit of data assimilation in your system, but it's still based on methodological models. And it's based on 11 models that run. And so those models, they relatively agree on the evapotranspiration and on the temperature, but for the precipitation, there is a quite large spread. Some of them will see a world which is much more weight than the others, which make that the spread is important. And because you have an important uncertainty on the precipitation, this is really the main source of uncertainty in the model at the end, even though the model might not be so sensitive to the precipitation. It's just because you do not constrain enough your precipitation. So if you would like to reduce the uncertainty in the model prediction, the very first things to do would be to work with colleagues in the meteorological labs to help them to reduce their own spread into their model. So now you can go to next slide. Something that I would like also to show you is basically in the context of saying, okay, if you want to do an MRV, you need to estimate how much carbon you have stored compared to a situation when you do not implement any carbon farming. But when you do that, you have to take into account that the time there is some change with time, and in particular the climate can change. And here it's the situation where I run in blue, it's still the control, but in light blue is the control plus 5 degrees simulation, plus 5 degrees in the climate. And so because it's hot, the climate is more warm, you have more decomposition of soil organic carbon. And so you at the end, you kind of decrease the soil organic carbon in that situation. And when you applied the scenarios of carbon farming in top of it, so you can go to the next slide, please, Marta. What you see, so it's exactly the same idea with, so light blue, I was telling you the control plus 5 degree increase, but in red, it's 20% of increase of carbon inputs plus 5 degree increase. In green, it's plus 50% of input plus 5 degree increase. And in pink, it's plus 150% of increase of inputs plus 5 degree increase. And what you can see here is that actually, if you would have considered the baseline with no climate change, which would be the dark blue one, you would have probably overestimate the capacity of carbon farming in that system. And you can see that at the end, even the scenario with 150% increase of carbon and with 5 degree increase, it's relatively close to the standard. So this is just a modeling exercise. It's still far from what will happen in reality, obviously, but it's just to underline that when you define some baseline, it's important to consider that those baselines, they are not fixed in time. They can also change because the climate conditions can change. A lot of other parameters can change. And the way you define your baseline in the context of an MRV system is very, very, very important. I think you can go to next slide. So yes, I would say that the take-home message we can have for the moment with the work we do at the MRV4SOC project is those hybrid monitoring system where you integrate in situ data, remote sensing, process-based model, etc. They can be like a very nice, robust tool for MRV approaches. It also it have to be very transparent. It is very key because, as you can see, there is a lot of details, and you can be easily lost in the details and make errors in the way you use the different data and remote sensing and or process-based model. But those approach can be very cost effective in an MRV context. You can say that the carbon sequestration, it depends a lot on, obviously, soil characteristics, management practices, climate conditions, etc. And those process-based models, they can be an interesting tool to test this kind of what-if scenario. So what if the temperature increased by 5 degrees? What if we have a big drought that make that the yields really are reduced from one year to another, and so on and so on. So this kind of approach is useful for MRV, but is, I think, also useful as a tool to kind of try to project what could be the effect of the carbon farming you want to implement and to do the best choice for your specific case. And then I think it is very key to keep in mind that the models, they are just, and the remote sensing and so on, they are just tool, and so it needs to be used as a tool. So when you have errors in one of the step, you have to be able to propagate this error in all the other steps to at the end be able to provide the end users with a projection that really is robust, because you consider all the possible error you have in the different steps of your systems. And I would like also to be very clear with something, is that we do not propose at all to use only remote sensing data and process-based model to do MRV or etc. It's very key that in our case, our system is also robust because we have sub-landscape approach where we have data and where we can calibrate all of the remote sensing product, and we can test our process-based model. But it is very important to take into account that if you want to upscale at the landscape scale, it has to be done in situations where you are more or less close to the initial situation where you calibrate your entire system. So I think it was our last slide, if I'm not mistaken, Marta. Thank you very much. I hope it was clear for everyone. And if you have any question, we are happy to answer them.